All right, welcome to section 5.6. We're going to be looking at complex numbers and how we're going to use them in this particular section. Really just trying to figure out what they are. So where we're going to use them in the study of quadratics, that's going to come up in a little bit in the next section. But right now, let's figure out what a complex number is. And in order to start thinking about a complex number, we need to think about how do we simplify radicals. Complex numbers come from a square root, so we need to remember how to simplify a radical. So first of all, we want to write the number under the radical as a product that includes a perfect square. So your perfect squares, if you recall, are numbers that are easily square rooted. So our perfect squares are going to be 1, 4, 9, 16, 25, and so on and so forth, right? These are the squares of the counting numbers. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so on and so forth. After we write that as a product, we need to simplify the root of the perfect square. So it's going to look like this. If I was to take the square root of 8, I know that I cannot do the square root of 8, but I do know that 4 is inside of 8. So I'm going to rewrite 8 as the product that includes a perfect square. So 8 is still 4 times 2. One of our properties for square roots says if I have a square root of a product, I can rewrite it as 2 separate pieces. And I know that the square root of 4 is 2, and I still have this square root of 2. We tried something like this. Oh, and that's it. That's the final answer there, 2 radical 2. So square root of 8 is the same thing as 2 root 2. If I had the square root of, let's go with 72. Now, not everybody's going to be able to see what the biggest number inside here that is a perfect square. However, I know that 72 is 9 times 8. And I can rewrite this as the square root of 9 times the square root of 8. But the square root of 8 I could have rewritten as square root of 4 times square root of 2. So I get the square root of 9 times the square root of 8, square root of 4 times the square root of 2. Right? Because 9 times 4 times 2 is still 72. So the square root of 9 is 3. The square root of 4 is 2. The square root of 2 stays square root of 2. So this final answer is going to be, not 36. It's going to be 6 square roots of 2. Now, what I said earlier is not everybody's going to be able to see the biggest number, but we could have said that 72 was actually 36 times 2 if you saw that. 36 is a perfect square, so I can rewrite this as square root 36 times square root of 2, which is equal to 6 times square root of 2. And you notice I get the same thing as we got before. All right, so this is the basics on how to simplify square roots. Always looking for perfect squares that are inside of the number under the radical. So let's move on to what we need to look at now, which is what is an imaginary number. And again, it comes from square roots, and you're going to have to use the last slide's idea in the imaginary numbers. So an imaginary number I, this is the letter that we give imaginary numbers. It is defined as the number whose square is -1, which means I squared equals -1. And this is super, super important for us. That is one of the most important pieces for us. Go a little highlighter over that, right? This is one of our most important pieces. And from that, that also means if I was to take the square root of both sides, the square root of -1 is equal to I, and that right there is our big second half of our definition for the I. So if I was to take the square root of -4, now you've been told for quite some time that you're not allowed to take the square root of negative numbers, but that's only because we didn't know how to beforehand. So the square root of -4 is equal to the square root of -1 times the square root of 4, using the same property we did on the last slide, which means the square root of -1 is I, and the square root of 4 is 2. Now we normally write this as 2I. So the square root of -4 is 2I. It's an imaginary number. Now don't think that imaginary number means they don't exist. They're actually a very important part of algebra. They get a bad name being imaginary, but they are not imaginary. They are actual numbers. So if we were to think about the square root of -8, so here's where we have to think about what we did in the last slide. So if I was to rewrite this, I would get the square root of -1 times the square root of 4 times the square root of 2, using the same property that we learned a moment ago. Square root of 4 is 2. The square root of -1 is I, and the square root of 2 remains the square root of 2. There we go. So the same property applies as we use the splitting of the square root in such a way that we can get the imaginary number outside and simplifying anything else that's important. And eventually you should just get to the point where if I looked at the square root of -16, you don't have to split it apart if you don't need to. The square root of 16 is 4, and since it's a negative, it's the I, so it's 4I. Let's see here, let's erase. So like I mentioned, you're going to use our understanding of simplifying radicals and combine it with the idea of the imaginary number to solve those types of problems that we just saw the examples for. So imaginary numbers lead into what we call a complex number. What a complex number is essentially every number can be written as a complex number, in the fact that complex numbers have the form a plus bi, and the a is what we call the real part. Call that the real part. And the bi is what we call is the imaginary part. That was supposed to say part right there. So if we looked at a complex number, 3 plus 7i, 3 is the real part, and 7i is the imaginary part. That really is it with what a complex number is. And like I said, every number can be written as a complex number. So if I had the number 7, 7 we know to be just a real whole number. We could write it as 7 plus 0i. We can write it as a complex number, even though we don't normally do that. So what are we going to do with a complex number? In this particular lesson, what we're going to do with a complex number is, first of all, graph them. When we graph a complex number, it's like graphing a coordinate. We're going to graph them on what's called a complex plane. Now, a plane is just like an XY axis. Here's this one, and here's this. We got a vertical and horizontal. The vertical axis is actually our imaginary axis. And then the horizontal axis is our real axis. And what that means is if I had the point or the complex number a plus bi it becomes the point A comma B. So when I look at the point 3 minus 2I, that becomes the point A, which is 3, and B, which is negative 2. And I can plot the point. Here's 3, here's negative 2. That right there, that coordinate is 3 minus 2I. Now, it seems kind of arbitrary that we do this, but what it leads to is something we can do with the absolute value of the complex number. That's coming up here in a moment. But plotting any type of complex number, negative 1 plus I, that's just the point. Well, negative 1 is your A, and positive 1 is your B. So we can go to negative 1, positive 1, and we can write in the point negative 1 plus I. And we get those points there. So as I mentioned, we're going to look at the absolute value. Now you have to remember what absolute value represents. Absolute value represents distance from 0. But in a complex number, it is on a plane, which means it's the distance from the origin. And if you recall, the distance from the origin is technically just the Pythagorean theorem. And we're going to use it really simply here. So the Pythagorean theorem says a squared plus b squared equals c squared, which actually just ends up being, if I was to write that down there, a squared plus b squared equals c squared, which means that c, if I took the square root of both sides, is equal to the square root of a squared plus b squared, where c is the hypotenuse. And if we were to draw a triangle in here, if we called this A and we called this B, just like we would have A plus BI, and if we were to find the absolute value, the distance from the origin to that point is going to be the value C. And if you notice, we can actually draw a right triangle here where side lengths of A and side length of B, which means the hypotenuse here is C, and that is the distance to the origin. So let's see what that means. If I was to find the absolute value of 3 plus 2i, 3 plus 2i, my A is my 3 and my B is my 2, and therefore the absolute value is going to be the square root of a squared plus b squared square root of 9 plus 4, which gets me the square root of 13. It is really as simple as that. The absolute value of a complex number is the distance from the origin, which is a very simple formula, the square root of a squared plus b squared. A couple more things that we're going to do with complex numbers. Now, complex numbers is kind of a deep thing. We can do a lot of things with it. One, we can find its additive inverse. And what an additive inverse is something that will add two things that will add to 0. So if I talked about 3 and negative 3 will add to 0. If I talked about 4 plus I, its additive inverse is negative 4 minus I, because if I added these two things together, I get 4 minus 4, which is 0, and a plus I and a minus I, which is also 0. So it's the opposites, the opposite things the opposite things here to make them add up to 0. Okay, so along that line, something else that we can do with complex numbers is we can add and or subtract complex numbers. And when we add them, we combine like terms. So if we said 3 plus 2i plus 6 minus I, I'm going to combine the like terms. I'm going to go 3 plus 6 because that's the real part, and I'm going to get 9. I'm going to add the i's together, so I get 2i and a plus a negative I, which makes a plus 1i, and I get my answer there. All right. The last thing we're going to do with these complex numbers is we're going to multiply them together. So we're going to multiply. Let's multiply the same ones that we just looked at. 3 plus 2i times 6 minus I. All right, so multiplication. We need to FOIL. So 3 times 6 is 18. 3 times minus I is a minus 3i. You get to actually think of I kind of like a variable in most of these cases. So now I've done the 3, now I need to do 2i. So 2i times 6 is a plus 12i. And 2i times minus I gets a minus 2i squared. If we simplify this from what it says right here, squared, I get 18 plus minus 3i plus 12i, that's a plus 9i. And I get minus 2i squared. But this is actually not complete because of one of the pieces from our definition. The definition is I squared equals negative 1. So right here, I have an I squared, which means this becomes 18 plus 9i. But then the I squared becomes negative 1. So I get a minus 2 times a negative 1 because I squared is negative 1. And what that becomes right there is a positive 2. So I get a positive 2 and a positive 18, which makes a 20 plus 9i. Now, why that is important is you should look, if you multiplied one complex number times another complex number, you should get a complex number. You should not get anything different than a complex number. So any type of multiplication, if I did 4i times negative 2i, we know that 4 times negative 2 is a negative 8. I times I is I squared. We know I squared is negative 1, so this becomes a positive 8. So make sure when you're doing 2 like this, when they're in standard form, that you FOIL. And also remember that I squared is negative 1. You must always get rid of that I squared. All right. That's going to finish us off. Hope you learned a little bit, and I will see you guys tomorrow.